So why do audio CDs have a sampling rate of 44.1 kilohertz? What's so special about that number? Well, 44.1 kilohertz is a little bigger than 2 times 20 kilohertz. And it turns out that 20 kilohertz is at the upper limit of frequencies that humans can hear. So when you're digitizing a signal, the sample rate must be at least twice the maximum frequency you want to recover. So for CDs, if we want to recover up to 20 kilohertz frequencies, then we need to sample at least twice that rate. So why twice? This is a concept that's called the Nyquist rate. So the Nyquist rate, so that says that we have to sample at twice the frequency of the highest frequency component in a complex wave if we want to recover all the frequencies building up the complex wave. So again, what's so special about this 2? So one way to think about it is if you look at the equation for a sine wave, so remember these are the building blocks for our complex waves, then it's a function f of t, where t is time, and where we have a term for amplitude, and we have a term for the frequency, and we have a term for phase. I'll explain in a moment what phase is, but by varying what these 3 quantities are, the amplitude, the frequency, and the phase, we can define a sine wave that is like this, or one that has much bigger amplitude, or one that has much smaller frequency. Any kind of sine wave we want, we can define with this equation. So really quickly, let me explain the phase term. So what does the phase term allow us to do? So suppose I have a sine wave that looks like this. By having a positive phase term, I can have that same wave but just shift it a little to the right. So all that phase term does is allow me to shift to the right or to the left. That's all it does. But in total, you can see that in order to define a particular sine wave, I have 3 things I need to define: the amplitude, the frequency, and the phase. What this also means, though, is that if I have an unknown sine wave, so suppose I just have some sine wave, in order to figure out what kind of sine wave that is, what quantities are the amplitude, the frequency, and the phase of this unknown sine wave, I have 3 unknowns to solve for in that equation for a sine wave. So that means I need to have 3 data points from this unknown sine wave to figure out what the amplitude, frequency, and phase of that sine wave are to be able to define that sine wave. So now let's consider, let's say I just have a particular sine wave here, and now this is the highest frequency component sine wave in the complex wave. So if I just represented a single cycle here, so that's over the period t. Now I want to recover what this sine wave is. I want to recover its amplitude, frequency, and phase. So that means I need to take 3 points at least. So one sample, another sample, another sample. So I need at least 3 data points here. And that also means I need greater than 2 samples per period t. As long as I have greater than 2 samples, then I'll have the 3 data points I need in order to solve for the 3 unknowns. Okay, so now if we have the we have to have greater than 2 samples per t. That's the same as having, so if we have greater than 2 samples per 1 period, that's telling us that we need a frequency that's greater than 2 samples over 1 over f, since period t is just 1 over f. Or in other words, greater than 2f sampling rate. And so this mystery 2 is now clear. So why, for the Nyquist rate, do we have to have 2 times the frequency of the highest frequency component in the complex wave if we're trying to recover all the frequency components in the wave? Well, it's because the sine wave equation has 3 unknowns, and so we need at least 3 data points or 3 samples over a cycle of each sine wave building up the complex waveform in order to recover all the frequencies in it. So there you go, that's the Nyquist rate.